Next up is Dave Baker, who is joining us from the University of Michigan. Tell us about categorical equivalence, substantive physical hypothesis.
All right, thanks, Jim. Thanks for putting this on. This has been incredible. Hopefully I've timed the run of this, so hopefully I'll get it done in time for plenty of questions. Should folks have them, which will be provocative enough to facilitate that. So I want to talk about an approach that it sounds like kind of people are kind of coalescing between, on the one hand, the point of view that David Wallace has put forward recently about math-first structural realism, and on the other hand, the point of view that several individuals, in this room, Hans, Jim, Thomas, as well as others, have kind of been looking at, which you might, I'm going to characterize as like the categorical equivalence approach, right? And in general, this talk is going to be critical of these approaches, but I want to say at the outset that I think that math-first structural realism is very attractive in its kind of core idea, and there's a version of it that I take very seriously as something that I might subscribe to, and indeed my credence in it increased after David's talk earlier today, which I thought was quite illuminating and helpful in understanding some of the things that I initially thought might not be super ideal about it. Okay, so where is this kind of like general confluence of approaches coming from, right? Well, what is it committed to? And I take it that the folks in this emerging tradition are scientific realists in what I think of as the minimal sense of that, insofar as they think a couple of things, one of which they're not the kind of internal realist Putnam. They think that empirically equivalent theories can differ in their content. And also, unlike von Frossen, they think that empirically equivalent theories can differ in how much evidential support they have. Whatever the reason for that is, combining those two things, I think, is like, I would say, the minimum commitments required to count as a scientific realist. I take them to be methodological naturalists, and that they tend to think that the methodology, at least of philosophy of physics, should be continuous with the methodology of physical science. They tend to want to think, this isn't necessarily true of David, but for the folks trying to combine these things, categorical equivalence in the sense of like isomorphism or duality as categories, plus empirical equivalence is sufficient for physical equivalence of theories, and that, and this is a commitment that David and Jim have certainly both put forward in various ways, that mathematical structure and not kind of like metamathematical or logical tools, quantification, stuff like that. Mathematical structure by itself is fully sufficient to express the content of physics. And I have some concerns about this generally. So I'm going to start out with kind of a bit of a broadside against the first argument that Jim kind of gives in favor of the categorical equivalence approach in his work, right? So he points to Gleemore's version of a translational definition of theoretical equivalence, and claims that it makes a mistake when it counts electromagnetism written in terms of the potential as equivalent, or as inequivalent rather, to electromagnetism written in terms of the field tensor, right? And he says, well, we need a notion of equivalence that will count those two things as equivalent because they're obviously equivalent. I don't think they're obviously equivalent. I think it's not a mistake that Gleemore's translational definition counts these two things as inequivalent, although I wouldn't necessarily endorse Gleemore's definition. I think there's a closely related claim, which is true, which is that electromagnetism written in terms of the field tensor should count as theoretically equivalent to the sophisticated theory that says, here's electromagnetism in terms of the potential, and in addition to that, I make the stipulation that the potential is not physically significant, right? But as Neil Dewar mentions in certain kind of asides in his work, and which I think is a very important insight that needs to be better recognized a theory's bare formalism by itself can't tell you whether to be a sophisticator, that is, whether to interpret one of its basic variables as not having physical significance. That needs to be something that you conjoin with the formalism of the theory or include in a kind of ordinary language scaffolding to the theory. It's not something that the mathematical formalism of the theory can tell you one way or another. So I guess I would question that kind of initial motivation for the view. But that said, kind of let's move on to the view itself. Okay. So the categorical equivalence approach, I want to understand it as a physical hypothesis in the sense that it's kind of conveying physical content, right? What it's saying is the world's structure is at most captured by theoretical structures that are preserved by relations of categorical equivalence, right? That could turn out to be true. It could turn out to be false, right? And in particular, you know, if we, for example, if we suppose idealizing that the empirical data, that the world is such that the empirical data is always going to be exactly the empirical data predicted by general relativity, right? Well, there's a couple ways that could be true. It could turn out to be true because the world has exactly the structure preserved that is given by all of the stuff that's categorically equivalent to general relativity, or the world could have more structure than that, right? And I think everybody agrees that it makes logical sense. It's not incoherent to suppose that the world could have more structure than the structure that is given by all and only the things that are categorically equivalent to general relativity. So that means that this is a substantive physical hypothesis, right? The categorical equivalence approach is saying something about what the world is like. It's contingent in every important sense except, you know, nomically contingent, right? And of course, this statement that the world is invariant, we might say, under categorical equivalence, its physical content differs, you know, from theory to theory, right? So in GR, you would say, okay, like assuming the theory we're working with is GR, then the categorical equivalence approach amounts to the physical hypothesis that the world structure is the stuff that is preserved when you take GR and consider all of the stuff that's categorically equivalent to GR, right? Different answer if you take Newtonian gravity and say, what's the stuff that's categorically equivalent to Newtonian gravity? So the question really is this physical hypothesis true in general or for all interesting theories? Now, when I ask this, what I mean is take a theory, suppose it's empirically adequate, right? Is the best interpretation of that theory one according to which the world has exactly the structure that is preserved by categorical equivalence? It's a pretty ambitious hypothesis to say that for a given set of empirical data, it's always going to turn out that the best interpretation of the theory is one on which the world structure doesn't exceed or go below the structure preserved by categorical equivalence. One aside here that's very important here, I think, in many ways, this is the crux of a lot of the issues that are going to come up. Of course, when we talk about categorical equivalence, we mean equivalence between the category of models of one theory and the category of models of the other putatively different theory, or putatively equivalent theory in this case, right? Now, a category of models needs a definition of arrows, okay? And the categorical equivalent approach tends to assume, and the results that have been proven would not go through unless each theory had a canonical category of models that's kind of like obviously the right one to use for that theory. And it's usually assumed, for example, that in general relativity, the category of models is obviously the one where the objects of the models of GR and the arrows are the isometries, right? What makes this obvious? Well, I mean, it's interesting, right? I don't think that should be obvious at all to folks who adopt for example, what Ehrman and Norton call manifold substantivalism as opposed to sophisticated substantivalism. But anyway, it's just taken to be obvious that within a given kind of like theory's mathematical framework, there's a privileged definition of what are the isomorphisms of that framework, and those are clearly supposed to be the arrows. I'm going to assume this for the sake of argument because it seems to be an assumption that the folks in this tradition take on. It's not obvious to me that it's compatible with, for example, certain kinds of sophisticated interpretations of isomorphisms or symmetries. So for example, in Dewar's work, again, on symmetries, he floats the idea that maybe in electromagnetism, we should think of the potential as being real, but two states that are related by a symmetry really, strictly speaking, have the same potential, right? What I take that to mean is something like the mathematical quantity that we use to stand for the potential, that's not an invariant quantity, but interpreted properly, it represents an invariant property, okay? If that's right, it's not so clear to me that he can just say that symmetries should count as like isomorphisms that characterize the theoretical structure, because there are lots of things that are going to, in a certain sense, not be preserved by those isomorphisms that we should, in a certain sense, be realists about. Right? Like Neil says that there's a sense in which we should be realist about the potential. Another thing I want to say here, by the way, there is a remark in Jim's survey article about theoretical equivalence where he says it might be that what we choose to be the arrows should be dictated by what's the right interpretation of the theory. He doesn't endorse this idea, but he says perhaps this is the way to go forward. If that's the view, then I very likely don't have any problem with it whatsoever, as long as everyone kind of understands that all of the real philosophical, interpretive, work of substantive physical interest is going to be done then at the level of asking what is the right interpretation of the theory that will give you the right set of arrows, okay? And if that's the case, then I don't think that, for example, proof of the equivalence of Einstein algebra GR and ordinary GR is itself of that much kind of like physical interest, right? So I take the proponents of this view to kind of disagree with that, but if they don't, then like that's we have much more agreement than I think that we do. Okay, so here's the categorical equivalence hypothesis as I'm kind of understanding it, right? The hypothesis is, to kind of boil down what I said a couple slides ago, the physical structure of our world, and perhaps we should relativize this to a given domain D because a theory might not be talking about the whole world, is captured by what I'm calling the CE invariant structure of our best theory, or our best theory of the domain that we're talking about. And what I mean by the CE invariant structure is the ontology agreed upon by all theories whose categories of models are isomorphic or dual or equivalent to T's category of models, right? And of course, including the right definition of the arrows. How do we evaluate this key question of whether that CE hypothesis is true, right? You might think like so the work in this tradition has so far seemed to proceed from the assumption that this is kind of like a question about how do we understand the semantics of our theories. No, I don't think that that's right. I think the right way to understand this question is, for any given theory, it's a substantive physical hypothesis, whether the universe has, according to, that is to say, whether the best interpretation of reality according to which that theory is empirically correct is one in which reality has as much structure as is left preserved by categorical equivalence, or whether it has more structure, or whether maybe it has less, right? So that's a substantive physical hypothesis. It needs to be evaluated by the standards of scientific epistemology, right? Now, empirical standards aren't going to be relevant to this since it's built into the definition of equivalence that we're using, that any two theories that are kind of putatively equivalent in this way are going to be empirically equivalent, right? So we're going to have to use theoretical virtues. I don't mean by this anything crazy, right? I mean by this our scientific common sense. That is, whatever norms we use to choose between theories that have the same empirical predictions. Okay, I'm not kind of building in any kind of specific theory of what these things are, but it's clear that in some situations, like between Einsteinian relativity and Lorentzian relativity, we know which one of those is good, we know which one of those is bad, right? That's our scientific common sense. We got to use that to choose whether the CE hypothesis is right or not. Now, is the CE hypothesis virtuous? Right, of course, like the commitment of the approach seems to be that for any theory that's physically of interest, it is going to be the most virtuous interpretation to suppose that reality is invariant under categorical equivalence, right? But this is not clear to me at all, at least in certain ones of the kind of paradigm cases, right? It seems like this, in a lot of cases, threatens to rob us of a physically intelligible or perspicuous picture of reality, right? I'm using perspicuous in something like the way that Thomas Muller-Nielsen uses it. That is, if you have a theory that's perspicuous, so look, knowing the folks here, I think everyone here agrees that when somebody like, Shelley Goldstein demands that, I love Shelley, by the way. But I disagree with him about the question of whether reality needs to be the sort of thing that I can paint a picture of in 3 dimensions, right? He has a view according to which reality's got to be the sort of thing that you can picture, and the basic things are things where if you look at them, if you draw a picture of them and you look at them and squint, you see big regular objects, right? I don't think that that's right. What I do think is a very reasonable demand that a theory ought to meet if it's going to be much good, right? That's not to say that this is knocked down 100% unbreakable, but it seems to me that an important virtue a theory can have is for there to be a clear and coherent explanation for how it could be possibly true, right? Now, everybody draws this line somewhere, and some draw the line kind of more liberally than others, but just like I don't agree with those who draw the line in an extremely draconian primitive ontology way, I think there's a mistake when folks seem to sometimes suggest that you don't have to draw this line, right? So I take David to be somebody who is generally very averse to drawing this line, but in this really wonderful interview with him in Schlosshauer's recent book on the foundations of physics, where he interviewed David, he asked, well, what about like information theoretic interpretations of quantum mechanics? And David's response, which I completely agree with, is that he's not sure that it's coherent to suppose that reality could be made up out of information anymore. I believe the line is any more than reality could be made up out of rumor or belief or something. I agree with that. Like, it from bit is an approach to the interpretation of quantum mechanics. I'm not going to say it's incoherent exactly. I'm going to say it's lacking in perspicuity in the sense that there's no clear or coherent interpretation for how that sort of interpretation could possibly be true. So it seems to me that if we require that reality has to be invariant under categorical equivalence, we're going to run into problems with perspicuity. So let's kind of look at a concrete case, right? So the general relativity version of the categorical equivalence hypothesis is that reality structure is whatever structure GR written up using regular differential geometry, the way that ordinary textbooks do it, and GR written in terms of Einstein algebras where the basic stuff is smooth functions, right? Rings of smooth functions. Reality structure is whatever structure those two things have in common. And it's just, it seems to me that it's just an extremely abstract and difficult to answer question. What is the structure that they have in common, right? Compare the clearer case of electromagnetism. I mean, you know, again, as I said before, it's not my view that electromagnetism in terms of the fields and electromagnetism in terms of the potential are equivalent. But a thing that I certainly understand is what is the common structure of electromagnetism written in terms of the field tensor and electromagnetism written in terms of the potential. The common structure is field tensor, right? They both have that. Okay. It's not so clear to me that it's right to say that there is a very full and intelligible set of structure that Einstein algebra and differential geometry GR have in common. In particular, you know, one of the things that they don't have in common is a common answer to the question of whether arbitrary smooth functions are more fundamental entities than space-time points, right? Of course, there are some functions that are of great physical interest, but there are also lots of functions that are just kind of garbage stuff that you can define ranging over the points. And so it seems to me actually that for, you know, if you're asking me, is a function, you know, is a smooth function that we ordinarily think of on the Einstein algebra, which is kind of getting things backwards, but a smooth function that we think of as being a function on spacetime, how fundamental is that? Should it be treated as a derivative entity or should it be treated as kind of one of the basic variables of the theory? I mean, I would say, well, it depends on the function, right? You know, a function that gives me something like mass or something like that, yeah, that's pretty fundamental. If it's a function that's like some jumbled together garbage, that's just an arbitrary function over the points, it's not very fundamental at all. To kind of take things a little bit further here, though, I would say if I compare a point of view on which points are not derivative entities, right, with a perspective on which there's no fact of the matter about whether points are more or less fundamental than arbitrary smooth functions, it just seems to me that the point of view on which there's no fact of the matter has an important theoretical bias, right? It's pretty difficult to understand the reality that it's putting forward, and it's not so clear to me that it's especially coherent. The categorical equivalence hypothesis, I think, is gratuitously weird in this case, and it makes it difficult to know which parts of our theories we can legitimately appeal to in our explanations. So another route that one might go to defending the CE hypothesis is to pull a move like the one that Gordon Bellott pulls in his Elvis fans essay, right? So like Gordon's asking the question, what are the kind of modal facts that we should say general relativity is talking about? He says, well, like this is the sort of thing where the modal facts should just be kind of fixed by the practices of physicists. Okay, so maybe we could say this is the same kind of thing, right? I wouldn't agree with this approach, but this is a way that the defenders of the CE hypothesis might try to defend it. Scientific practice simply tells us that physicists are talking about mathematical objects up to categorical equivalence and not drawing distinctions that are more fine-grained than categorical equivalence allows. But it's not clear to me at all. It seems to me that ordinary physicists do tend to be inclined to characterize reality in terms that are not left invariant by CE mappings. Indeed, you know, like if you think about Newtonian gravity, physicists tend to impute significance to geometric properties that differ between Newtonian gravity in its ordinary form and geometrized Newtonian gravity in Newton-Cartan theory. you could probably get a physicist to agree that these are equivalent, to be clear. But I think you would do that. I mean, like, look, if I take two theories that are empirically equivalent, I'm pretty confident that I can get 95% of physicists to agree that they are equivalent, full stop, by appealing to those physicists' anti-realist tendencies, right? Physicists have been raised in a soup of positivism. And so if you want to get them to agree that some things are physically equivalent, it's easy to do. But I think that's cheating, right? I think the only way that you could get a physicist to agree that those theories are equivalent is by appealing to scientific anti-realist tendencies. And I take the defenders of this approach not to want to go that far. Now, okay, so this is kind of the conclusion of this issue about whether the CE hypothesis is virtuous. There's one more issue that I want to go into before I finish. So here's a question about this approach. So as I was saying, right, Weatherall and Wallace share this view that physics doesn't need a richer language than mathematics in order to state the real physically significant truths. And in particular, it doesn't need predicate logic in addition to mathematics. Wallace does mention in his stating structural realism paper that there's a version of math first structural realism that you could come up with that's kind of a hybrid view that says, well, there's irreducible mathematical representation, but in addition to that, we need a language that, in addition to the mathematical terms, has predicate logic terms, right? I think that's got to be the right view, and the view where you don't need the logic terms is clearly wrong. What I'm going to say here, I think, is also a concern that applies to Jim's views from his whole argument paper about, again, the idea that like the basic tools used for representation in physics are mathematical solutions to a theory and not logical terms that we kind of add on to those, right? My concern about this is how does this give us the expressive power to make statements about substructures of a model or a physical possibility? So for example, right, suppose I take a solution of general relativity that we would ordinarily say describes two black holes. Now, how do I say something about one of the black holes and not the other, right? So how do I say, oh, this one has a greater mass than the other, or this one and not the other one is charged, right? How do I say that kind of thing? Using purely the resources of differential geometry, purely the resources of the mathematical language in which GR is written. I don't see how you can do that, right? I need to use logical vocabulary to quantify over or name stuff inside the model, right? I need to be able to name points or regions or singularities or something in order to say, I'm talking about this black hole and not this other one, right? So it seems clear to me that mathematics by itself is not a rich enough language to express all of the physically significant truths that are there in the theory. One possible response, right, is perhaps it's only a sort of roughly true or approximately true thing to say that there are two singularities and two horizons. To be clear, I actually take this really seriously as a possibility anyway for like a number of reasons. So I'm not saying that this is crazy, but I think it needs to be understood what kind of a bullet is being bitten if one takes this, I mean, we might say not just math first, but math only picture to interpreting theories, right? So perhaps it's just not, strictly speaking, part of the structure of the world that in this solution, there are two singularities and two horizons and stuff like that. Instead, right, or that, this one is more massive than that one, or that this one is charged and that one is neutral. Instead, maybe what's going on here is that what Wallace calls the predicate precisification of the theory would have you say there's two singularities and two horizons, right? we kind of take the mathematical theory and we come up with the predicate logic theory that does the closest job of getting at the same kind of stuff that's being represented mathematically. We could try to do that. And we end up with something that is decent. It's a decent approximation to the real mathematically representable reality, but strictly speaking, it's not accurate or not 100% accurate, right? So maybe that's the status of these kind of quantificational claims. I wonder how plausible that is, though. Again, I mean, I think there might be good reasons to take this step and bite this bullet, but it does seem to me to be a bullet because it seems to me intuitively like there are two black holes is part of the physical content of that state. Some more expressions that seem like they'll be difficult to handle without introducing logical vocabulary in addition to the mathematical vocabulary, right? If I say like, the system is in a momentum eigenstate, I seem to need to be able to, so you might think of solutions of a quantum theory as being akin to atomic sentences or something like that, right? If that's the way to think about it, well, I'm going to need to do a disjunction of those in order to say the system is in some momentum eigenstate, but I'm not telling you which momentum eigenstate it's in. Again, it seems like clearly a physically significant statement. If this system were a little cooler, there would be a phase transition, right? It seems like, again, I need connectives between those atomic sentences. And in this case, actually, like modal logic connectives. So pretty heavy logical machinery in order to say this clearly physically significant and true statement. There's not going to be a solution of the theory's equations that is sufficient by itself to express these claims, right? So like Ladyman and Ross in their initial statement that kind of was one of the kind of prototypical ideas that I think is behind math for structuralism. They said, well, look, if somebody asked us what the physical content of GR was, we would present them with the solutions of the field equations. And if they asked us to say more, we would not say more. We would just say that's the physical content of the theory, is these solutions. Well, if I ask you, how do you say if this system were a little cooler, there'd be a phase transition? Which solutions are you going to hand me to say that? No, that's a statement that involves connectives in addition to the content that is carried by the solutions, right? And the same goes, I think, for that earlier example about black holes. So at the end of the day, where do I land, right? As I was just saying, I am attracted to math for structural realism, but only in its moderate form, right? That is only in the form that says, and it sounded to me in his talk earlier, like maybe David is when he was saying like, we seem to have mathematical representation and linguistic representation going on in our cognition and, from when we were children and stuff like that. Maybe the mature version of the view is that you do need both types of representation, right? Mathematical representation and language-like representation that we can think of in terms of logic. I'm attracted to that version of math for structural realism, but I think the version that says kind of what you might call math-only structural realism, where the content of physics is conveyed, again, Ladyman-Ross style. If you want the answer to what the theory says, plop down the solutions and leave it at that, right? That seems entirely untenable to me for the reasons I just talked about. And for the reasons I talked about earlier, this, I'm less sure of this, but it seems to me that I'll put the dialectic this way. If the CE hypothesis is starting out with the idea that if you give me the solutions of a theory and its empirical content, I can tell you what the arrows are just from that, right? And then starting from that machinery, I can answer questions about whether what's categorical equivalent to my theory. If that's the view, then I find that view extremely implausible, right? In the sense that it's a substantive physical hypothesis, and it's a substantive physical hypothesis that in many cases is not going to pass the smell test of scientific common sense compared with its competitor. Now, if the view is, if I hand you a mathematical theory and its empirical content, then first you've got to use your scientific common sense to do the hard work of interpreting it and figuring out what its real physical content is. Then from that, you figure out what the arrows are, and now you can figure out what's categorical equivalent to it. That is much less questionable to me. But then I would say the folks who have drawn conclusions on the basis of categorical equivalence need to say a lot more about why the arrows they picked are the right arrows, what interpretation of the theory justifies choosing those as the arrows and not other possible choices of the arrows. If that's not the approach, on the other hand, and if the approach is, if I give you a theory, I tell you its empirical content and its mathematical models, then I know what the arrows are, and then I know what's categorical equivalent to it, and reality is only the stuff that is invariant under categorical equivalence. That to me seems like an extremely implausible substantive scientific hypothesis. Okay, that's what I got.
We have 22 minutes for questions. So David, Jeff, Emily.
Oh, that was great. You definitely succeeded being provocative, so I love it. Get back in the queue. Where should we go? Let's talk about the what physicists find as equivalent, because I think maybe it's a sociological thing. I think I quite strongly disagree with that, what physicists think. I mean, the using Cartan case is kind of fiddly to play with because it's not that much used in mainstream physics, but there's a closely analogous case that is, which is geometrized versus non-geometrized ways of talking about general relativity. And if you're looking at Weinberg writes a textbook on GR that hardly mentions the geometric way of thinking at all, and very much is talking about GR as a spin-2 field or that kind of space-time. And Mr. Thornton-Wheeler writes a textbook on GR that's incredibly thick with geometry. But none of these people talk as if one of them right and the other's wrong. The conversations about those are all pragmatic, they're what's pedagogically most helpful, what's the useful way to think about it. They're casually going back and forth between them. I mean, it's the same thing with Sean Cowell in some bits of his work will talk about geometry in a geometric way, in some ways just throw it into a flat particle physics way. Or if you want an even more extreme example, look at the way string theorists talk about ADS-CFT. I mean, those two halves of the duality are wildly different in this kind of way, and yet, I haven't read this entire literature; it's much too big. But I've gone quite a long way into it. I've never seen anyone of the subject suggest that there's substantive matter as to which of the ADS or CFT sides of the duality are correct, except insofar as they're questioning whether the mathematical result exactly is an emergent or approximate result.
Well, I mean, okay, so good. So we got to be careful to prize apart two things, and I think one of them is going on in the ADS-CFT case. So the GR case is interesting, right? Like, I don't know, like I found that the kind of differences between, for example, like the Weinberg textbook and a lot of other textbooks are the kind of differences where like physicists don't like to argue in print, but they do like to argue in person. And, like there are a lot of people who will say that the Weinberg book is of great interest as a teaching tool, but physically kind of like deceptive. In my experience, I don't know,
Like say it's false.
So false in this kind of case is an interesting thing, although they wouldn't draw this distinction, but of course, as you know, right, there's a distinction between stuff that is true in more natural terms and stuff that's true and written in less natural terms, right? So I mean, I guess, with the ADS-CFT case, though, it seems to me that the right way to understand what's going on in the community is that they see significant theoretical virtues arising from supposing that in this case, reality is the stuff that's left invariant by the duality, right? And there are things that they can do by making that assumption that they see as kind of important to the explanations that they're trying to provide, and that it doesn't seem like they're kind of able to do otherwise, right?
So I've read a bunch of accounts of the ASCFT correspondence.
Yeah.
If that was correct, you'd expect to find statements along the lines of, and so we see this mathematical equivalence. So we might be led to a bold conjecture that we should actually regard these not only mathematically, but also as physically equivalent. And this would do the following useful theoretical work. You never find that. It's like the mathematical equivalent, same theory, let's move on.
Yeah, I mean, like, so yeah, it's a good point. Like, I think in that case especially, it's a good point.
Jeff?
I'll read you in the queue.
You're already there.
Yeah,
yeah.
No, just infinite cycle.
Yeah, I can't imagine how this isn't going to fill up the rest of the time.
Your question?
Let's do it.
So, right, what's at stake here? What's at stake here in part is what we take to be a physical theory. And I don't think we're going to have a canonical notion of that. This is physical theory once and for all. These are the necessary and sufficient conditions for something to count as physical theory. And so to some extent, we end up talking past each other. What I take the physical theory to be, to a large extent, depends on what I want from my physical theories. But if I want predictions for my physical theories, then I'm going to want something that's at least partially interpreted, not just pure mathematics, but I'm going to want something that gives me predictions. If I want explanations for my physical theories, say I'm going to want something that's even more richly interpreted. If I want to do mathematics, I consider structural mathematical similarities, right? Like categorical relationships between alternative mathematical models. Then I might understand the theory to be a different thing. So I think there's some talking past each other that's taking place here, because people have in mind different notions of what a theory is for the purposes at hand. And so that's part of the suggestion. A notion of physical theory, like the one you called math only, where we don't enter into the what David calls predicate precipitation process at all. There's stuff we can do with a theory like that, right? It's a mathematical model, we can kick it around, we can see what other mathematical models it has various structural relationships to and such. But in terms of explanation and prediction, it's just not going to be very informative. But somebody still might want to say that's quantum mechanics in a concrete case, and then everything else is an interpretation of that mathematical structure. And there are various rhetorical reasons somebody might want to do that too. And so what I wanted to suggest is that there's not a single canonical notion of physical theory on the table here. We use the notion of physical theory in different ways, and properly so.
Yeah, I think that's right. So I guess my riff off of that would be a couple things. I mean, one is, of course, like the distinction between a theory and an interpretation of the theory is one that gets kicked around a lot, especially in kind of the quantum mechanics stuff. I mean, I tend towards the point of view that insofar as that notion makes sense, it's something like the following. You might draw a distinction between kind of a theory understood as the usual way it's written up mathematically plus its empirical predictions. And then my point of view would tend to be the right interpretation of that theory. So an interpretation of it is kind of like a fully spelled out theory. And then the right interpretation of the theory would be what would be the most reasonable hypothesis to believe about which fully spelled out theory is true if the empirical predictions of the theory are correct.
I would go a step further than that. I really don't know how to separate the interpretation from the mathematical structure of alternative formulations of quantum mechanics, things that are called interpretations. But that's because I'm interested in both prediction and explanation there. But that's what makes it hard to take the mathematical formalism apart from the what's more standardly understood as the physical content.
Yeah. Yeah. I guess the other thing that I would just add to this, Jeff, is I think that what I take myself to be talking about here is theories where they are ready for us to draw conclusions from them about what the world's structure is. And if the ambition, for example, of the proof that regular formalism GR is categorical equivalent to, or categorically dual to Einstein algebra GR, if the ambition of that proof is not to say that if the predictions of GR are correct, we should draw the conclusion that the world's structure is the structure shared in common by those two formalisms, then it's not clear that I have any quarrel with drawing that conclusion. But if I'm supposed to draw the conclusion from that proof that if GR is right, the world's structure is the structure that those things have in common, then I've got a problem with it.
Yeah, and I think you made that clear in the presentation. This is a set of issues we should all be arguing about until we get it settled.
I thought we had.
There may be one or two.
Yeah, thank you. Yeah, I find it helpful to think about the suggestion of thinking about categorical equivalence as a substantive physical hypothesis. And I guess I also wonder if maybe empirical standards could, in some indirect sense, be relevant. Like, I guess one reason that a physicist in particular might care about theoretical equivalence is because you might think that if two theories are non-equivalent, then they're potentially going to determine like different research programs, which will ultimately lead to different physics. And then you could imagine that like one of them will be sort of vindicated by the empirical success of its research program, and the other one won't be. So I guess, one question here is, has there ever been, or is it conceivable that there could ever be a case where categorically equivalent theories lead down different routes in terms of research programs? Also a higher level question in the background here about when we're assessing theoretical equivalence, are we supposed to be suspending disbelief and imagining that the theory in question is the complete final theory, or should we be kind of leaving room for the possibility that later theoretical developments are going to sort of shape that judgment?
Yeah, let me take the second part of the question first, because this is definitely an issue where these dialogues can get delicate. My approach generally is, of course, one should keep in mind that a theory that we're talking about today is at best an approximation to reality. I tend to think that in like 90% of the cases, the right way to do that is to ask what would be the right thing to conclude about reality if the theory were exactly true, and then say approximately that within the domain of the theory. I know it's one of the biggest disagreements between me and Wallace. Okay. So on the first part of the question, which is really important. It's a good question. I mean, I don't know whether, for example, the parastatistical parton theory and the early pre-QCD quark theory would count as categorical equivalent. I mean, they're probably not spelled out with the degree of mathematical rigor that would be required to kind of answer that question. But that's a clear historical case where you had a pretty interesting sort of equivalence between the two, and they one of them turned out to be the genesis of a good research program. I gather that there are kind of like ideas for using Einstein algebra based stuff, maybe for quantum. I don't know anything about this, but that might be a kind of thing. I don't know, I think that the quark and parton case might be an example, but then it was a case of theories that were kind of like early enough in their development that you didn't have. So I guess part of the problem is that when you're talking about things that are going to lead to research programs, you know, a lot of the time those are theories that aren't mathematically completed enough for categorical equivalence to be a kind of like a good, you know, way to talk about them.
Great, thank you.
So this is a finger.
It's just a very quick comment.
Okay.
Just very quickly, and wasn't this exactly what Feynman had in mind when he talks about different formulations of the same theory?
Oh, yeah, yeah.
Physicists need to know them because
Exactly.
one of them leads to the new theory rather than the other.
Exactly.
Yeah, although I guess I was thinking there's a sort of psychological version of that where it's just one of them's easy to think about, but you might also think that if they're actually physically different in some sense, then one of them is more right and thus is more likely to lead you down the correct.
Yeah, that's right. Although I'm a little skeptical of the idea actually that a theory of a particular domain is obviously going to be a better approximation to the truth in that domain if it leads to a better theory of other domains, right? Like I'm not sure that that's going to generally be true.
Ellen?
Yes, thanks for the talk. I have a question about the categorical equivalence hypothesis that you put forward in this talk. So seems to me that so this hypothesis the word structure is only captured by theoretical structures preserved by categorical equivalence. I'm not entirely sure because it seems to me that the theoretical structures preserved by categorical equivalence and the word structure, these seem to be structures at different levels. It seems to me that whatever theoretical structures that categorical equivalence preserve should be some categorical structures of the categories of the models of theories. And that's presumably tell us something about, maybe the two theories have the same amount of symmetries. And we use those models of theories to represent some structures of the world. But that's kind of a relationship between the models of the theories with the world. In some sense, the models of the theory represent some structures of the world. So it seems to me that those two kinds of structures are on different levels. So I'm not.
Well, yeah, so the structure of the world is physical stuff, right? And the structure, the categorical equivalence invariant structure of the theory, as you're kind of pointing out, right? That's like mathematical stuff, right? That's like mathematical structure. Is that kind of like, I take it that's the point? So I guess I mean, my inclination would be to say the same kind of thing that David said in his earlier talk, that there's going to be some kind of relation that characterizes the way that a mathematical structure represents or stands for the kind of structure that the world has. And we kind of take that for granted, probably in large part because we don't have the resources to define what that is, because it's something that we can never kind of get away from, right? We're always representing. So we can't with 100% from the ground up say what representation is. Right? But yeah, like the view is that whatever representation relation folks are saying there is between mathematical structure in a theory and physical structure in the world, the CE hypothesis is that representation or that representation relation holds between the CE invariant structure of our best theory and the physical structure of our world.
I think you may be talking past each other a little bit. I think Ellen's point has more to do with the category is going to reflect much more than just the structure of our world. It's got all this modal information about multiple worlds, right? And so there's a kind of, this is suggesting that what's preserved between these whole categories is somehow something about a particular object in the categories.
Thanks, Jim.
Yeah.
Thank you, that's helpful, yes. Right, I mean, like, so I take it that what's going on there is the distinctions that the category of models of the theory draws are going to be distinctions that we think are real between our world and other physically possible worlds. And that's the sort of way in which this representation relation applies to that kind of question, right? So like, two models in the category of models are going to count as different models in that category if the worlds that they describe are, you know, different physically possible worlds in some way, right? So yeah, it's true. When I say of our world, I'm kind of like I'm glossing over something. Really, the theory is representing all of the worlds that are possible according to the theory's laws, and that's really what I should be saying. The physical structure of all the worlds that are possible according to the theory's laws. That's the structure that's given by the CE invariant structure of our best theory. Good.
And Khan's had
I was just going to say, I have a section on this in my talk that hopefully will clarify that very issue a little bit. So maybe we want to discuss this after.
Okay, great.
The plenary discussion.
Harry.
I'm gonna wait for the roundtable.
Okay. Clara.
Yeah, thanks, Dave. So on your slide, when you were talking about differential geometry and Einstein algebra, you had this question where you said like, well, what this categorical equivalence approach doesn't tell you is what the structure in common is. And I just wanted to ask if you could say a bit more about what you think it would mean to pinpoint what that structure is that they have in common, other than just giving the kind of relationships that this categorical equivalence approach.
Yeah. I mean, right. So I am certainly proceeding from an approach on which there's a more general notion of saying what the world is like than kind of like, I'll put it this way, right? Like, I allude to one further criterion that you might want in this, which is to say, for example, which entities are derivative and which ones they are derivative from, right? I mean, I think it's itself a substantive physical question whether the world has building blocks, but it seems to me that hypotheses on which the world has building blocks have advantages over hypotheses on which the world doesn't have building blocks. And it seems to me that if you take a more ordinary picture of GR and contrast it with the CE hypothesis, the ordinary picture of GR is one on which the world has building blocks. And it's not very clear to me that on the CE hypothesis version of GR, the world has building blocks, right? Because the CE hypothesis version of GR is going to be one on which there's just no fact of the matter about whether functions or points are building blocks.
Can I try to press this point just a little bit? It's time for coffee, so I just want to say that you have this. What is this structure? It seems to me that suppose I told you what the structure was. I'll give you some new theory. Two possibilities. One is categorically equivalent, or equivalent to whatever the right notion of equivalence is. Categorically equivalent to both of these other two, or it's not. If it is, then nothing's been accomplished. If it's not, then I'm not doing either of these theories any longer. And so it seems to me as if what you're asking for here is actually for us to come up with some other kind of theory that's not general relativity, or Einstein algebra GR. And moreover, sort of in the background is this idea that that had better not be categorically equivalent to anything that looks too gratuitously weird, or else it's not going to be an adequate theory. And so you're sort of imposing this additional constraint on physical theorizing that, you know, whatever we're coming up with can't have sort of alternative formulations lying around.
So I guess that my view is, right, so I knew that this was going to be a communicative difficulty with a big chunk of this audience, right? So I'm approaching things from a perspective according to which if I hand you two categorical equivalent pieces of math that are combined with empirical predictions, there are kind of like three possible hypotheses I can put forward. One of which is this one, and you know, this one matches reality structure. Another one is this one matches reality structure, and another one is the common structure of these two matches reality structure, right? And you know, I understand that folks who think that CE is the way to determine what structure theory represents are going to say no, like only the third one is even a thing that makes sense, or something, right? I take it that's kind of.
Oh, I would say that the first one and the second one are both true.
I would say the third one is incoherent.
Yeah, this is interesting. I mean, we definitely run into a kind of like. I guess that one of the things that brings us to an impasse here is as I'm kind of alluding to here, I think that what primitives you choose matters to what your theory is saying. Some people don't think that what primitives you choose matters to what your theory is saying. Or I guess I would put it this way. I think it's possible to put forward a hypothesis according to which what primitives you choose matters to the content of your theory. Right? I mean, I take it that your approach is, no, like that's not possible. It's not possible for me to put forward a hypothesis according to which it matters that I chose the differential geometry type primitives as opposed to the Einstein algebraic primitives. But
I mean let's save that for the roundtable because otherwise we're going to get coffee before Hans talk. All right, thank you so much, Dave.
3:45.
3:45.
my parking from the airport.
Is there anything,